why to go to Mars. Next is the asteroid belt. When you think of the asteroid belt, I think of movies like in the Star Wars movie where Han Solo is flying through the asteroid field. Okay, that is not how it looks. Okay, the asteroid field that are in the movies have asteroids that are really close together. The asteroid debris field that we have is a rock, and then millions of miles that way, another rock. And then thousands of miles this way, another rock. It is very spaced out, much more than what is a good picture. This picture puts all the rocks really close together so you can see it, but really if we took a picture of the asteroid field, you might get one rock and not see anything else. So it's not very dense. We know this because we've sent lots of probes past that and never ever hit anything nor accounted for hitting something in the asteroid belt because it's so open a space. There are large rocks, and some are very large, up to 1,000 kilometers across. And in particular, that one is named. It actually, it was part of the asteroid belt. It is now defined as a dwarf planet because of its size. It gets into that intermediate stage. A lot of people thought it may have been a planet that broke apart, but more people now feel that it was the potential additional planet that just didn't form correctly. A lot of energy and time is invested into looking at them and tracking the ones that are larger. They are named and tracked to make sure that we know if it is going to come hit us or not. And most of the time, they're kind of orbiting in their own orbit. The only way that it would actually come towards the Earth if two of them hit together and bounced off like pool balls and actually just ended up coming towards us, it would be a lot more chance than anything else. But most of them are orbiting around the sun themselves. The outer planets are so much larger, and so you can take a look and see of the inner planets, the Earth is the largest, and then you see the others, Neptune, Uranus, Saturn, and Jupiter. They're just huge in terms of size. Jupiter, the largest planet that we know, has a very fast rotation, and it goes around the Earth at almost 12 years it takes to go around the Earth. What we're actually seeing are clouds. And there is a very prominent feature right there that sits on the planet. Okay, it's called the eye. And really, this thing is larger than the Earth. That spot is really a hurricane that is happening. And from the earliest times we've had telescopes, that hurricane has been there constantly going. Now, for the hurricane to actually exist, that means there's some energy coming up that's disturbing that area, but it's been pretty constant right there for a very long time. And so here is the Earth size to that hurricane. It's larger than the entire sphere of the Earth. Okay. Now, it's been constant for all we know, but what we have seen, and I've read some articles about this, the spot seems to be getting lighter over the past decade or so. And we don't know what that means, but it's actually becoming less dense than what it was in the past. Jupiter has over 63 satellites. There are 4 of them that are the biggies. Io has volcanic activity, slightly larger than the Earth's moon. Europa is smaller than the Earth's moon, but we know that there's tectonic activity. It's covered in ice. Ganymede, larger than Mercury, has tectonic activity. And Callisto is also one of the big ones. If there was one place that people had to put money down and bet where might life actually exist in our solar system, it would probably be Europa. That's probably the best money if you think about an evolutionary model in which all you need is liquid water. Europa is full or covered in ice, but we know it has tectonic activity. We know it has magma. There's some place between the hot magma and the ice layer on top, there should be water. And with that magma, we see under our oceans very specific life that is derived from the gases that come off of volcanoes, and it doesn't actually need oxygen. So the combination of all those things actually develop the most likely evolutionary conditions in which life might arise. And so from a truly atheistic perspective, this is where they might think about. We have several plans developed by JPL, which is a division of NASA, for a mission to go to Europa with drills and little submarines to drill down to the water layer and use submarines to find the potential of life. Although NASA has lots of plans, lots of missions planned that aren't funded, and this one is not funded. But this is where a lot of scientists would like to look to see if there were evidences of life within the solar system. Jupiter and really all of the outer planets have a little tiny ring of dust. Now Saturn has a spectacular ring, but all of those have a ring. It's 1,300 times larger, but only 318 times as heavy as the Earth, which means it's really, really low density. It is mainly made up of hydrogen and helium. Okay, it may have a small rock core, or it may be just solid gases due to gravity. This is kind of an interesting thing, though. We take in the sun's energy, and that powers a lot of things on Earth, including plants living, and then we eat off the plants, and animals eat off the animals that eat the plants. And so a lot of the energy that runs the Earth is coming from the sun. So we absorb energy. Jupiter, on the other hand, actually emits more energy than it absorbs from the sun. There's heat coming off of it. It is made up of the same gases as the sun. It is just not massive enough to actually become a sun. If it actually had a little bit more size or a little bit more mass, we would have two stars in our sky, the sun and Jupiter, just like the suns of Tatooine, where you look up and you would see two suns. And so there are a lot of systems that have two stars in the same solar system. We were on the edge. Jupiter was almost there, but it isn't. And so it's like right on the edge of having been a star. Saturn is very Jupiter-like. It is also hydrogen and helium, and it also gives off more heat than it absorbs, but just slightly. It's a lot of clouds, but it's spinning so fast, those clouds look like lines. It has up to 30 small moons. One of them, named Titan, is the only moon with an atmosphere, but it's really too cold for us to think that life might be there. One of those moons is right perfectly placed. And because Saturn is so large, it takes that moon and it has lots of stresses because of the gravity. What's happening is that moon is being kind of broken apart as it goes around Saturn, and it's spewing off material, the material that makes those rings pretty spectacular. The rings are really, really thin, but very, very broad. The reason we know that is because every so often, Saturn's rings are like this to us. Every so often, Saturn will get lined up just like this, where the rings are right towards us. We totally lose the rings. We can't see them anymore because they're very, very thin. But as soon as it tilts up, we see the ring system again. They classify this, and people who study the rings actually have like A through Z rings that they study. But you can see three major parts: a bright part, a dark part, and a bright part, but they even get broken down. After studying and then sending probes, we know that there's dust, little rock, some ice that make up those ring systems, and they're being held in place by the gravity of Saturn. But remember, all of the gas planets have a ring. Saturn's is just spectacular. Uranus and Neptune were discovered by telescopes in 1781, Uranus, and in 1846, Neptune. Actually, Neptune was predicted to have existed because every so often Uranus was, the other planets were kind of off a little bit, and they mathematically calculated that there should be something with a lot of mass, another planet that would affect the other planets, and so Neptune was discovered that way. They all have rings, and Neptune has much more violent storms versus the planet Uranus. Pluto, here we go. It was also discovered by telescopes. It was discovered in 1930. Okay, so from 1930 to August of 2006, it was a planet. After 2006, it is not a planet anymore. It is a dwarf planet, and I love the cartoon. Have you ever had Thanksgiving dinner where you got moved to the little kids' table? That's what happened to Pluto. Got moved to the little kids' table. Okay, here is why. Okay, there was an astronomer that discovered another body in our solar system. Okay, and it was found in 2003. His initials were UB, and it was the 113th item to be found that year and cataloged. And he discovered this body, and just jokingly, I think, he named it Xena, Princess Warrior, and found later a moon that I can't even remember what Xena's sidekick's name was, but named that the sidekick. Okay, and I think that was part of his problem. And so, after finding it and studying it a little bit, he found that it was larger than Pluto. And so he demanded that this be the 10th planet in the solar system. The Astronomical Association said no. And he said, wait, it's bigger than Pluto. And I said, yeah, well, we're not going to name a planet Xena, Princess Warrior. And so he went back, and if you take a look at the articles, they changed the name to make it, a more proper name, but that didn't help. And so everybody got together in 2006 and tried to distinguish what was a planet and what wasn't a planet. And this is what they did. They came up with a definition. A full-fledged planet is an object that orbits the sun, boom, it orbited the sun, and is large enough to become round by its own gravity, and it has dominated its neighborhood around its orbit. Okay, so it had to be round, okay, had to orbit the sun, and it had to have circled around the sun enough to hit all the stuff in its orbit so it isn't hitting into things. And it has to be dominant. Pluto didn't meet the criteria in that it wasn't absolutely round. It's still hitting things in its orbit. And this is more importantly, its moon is almost the same size as the planet itself. And so it actually is almost a double planet that is orbiting around itself. And so when you take all that into account, they decided to classify it with these smaller bodies, including the Xena one and about 40 other planets that are now considered dwarf planets. They're much larger than just an asteroid, but they're not at the level of a planet. We have lots of dwarf planets, and so in relationship to the moon, some of them are even comparable to the moon, but Pluto wasn't even as big as our moon. And so as we take a look at this, there are several of the dwarf planets that were found in at different times. One indicator that is pretty kind of stands out is that when you look at the orbits of these, and some of the dwarf planets are close to the sun, some are further away than the planets that we know, but take a look at the side view. This is where all the other planets lie. These are the elliptical orbits of the dwarf planets. They just don't fit the others. They're on totally different elliptical planes. And so that's another indicator that they just behave differently than everything, so they should be in its own different class. And so the dwarf planets now exist, and there are lots of them out there that are being found even today. The last thing that we're going to look at is the moon itself. Okay, it's relatively close, 384,000 kilometers away. It's about a quarter the size of the moon, and it circles the Earth at about 29.5 days for it to go around the Earth itself. The rotation keeps pace exactly with its revolution. That means the face of one always gets pointed towards the Earth, and as it goes around, its day and its year is in perfect sync. So that means we only ever have one half of the moon facing us. There is the dark side of the moon that is always on the other side, and we never see it. We'll go to an animation to show you why that actually is. The moon does not produce any light, nor does any of the planets. It reflects light from the sun, and the moon is relatively light in color, so it becomes bright in the night sky. The moon goes through phases. We'll show a little animation about that.
We're going to focus on the four.
Okay, so we can see during the month, the amount of moon light that we see reflected to us becomes little to big to a full, and then it wanes. So it talks about waxing and waning, but it is because of the position of the moon versus where the Earth and the sun is. Okay, and why we see that change over the period of time. Now, every so often we get what is called an ellipse. An eclipse. But we said that the Earth and the moon kind of get in front of each other every month. Well, why in the world do we not have an eclipse every month? Okay, because of this. The moon and the Earth are not in line. See how the moon is below, the Earth is above. And when the moon gets in front, the shadow is above the Earth. Okay? There is only one point on this orbit in which the Earth and the moon are in the same level. And so there is a tilt where the moon is, and as we go around, there are only 2 times in the year in which we all align. Now, a solar eclipse happens when the moon blocks out the sun. So we've got the sun, the moon, and the Earth. And so the light coming here gets blocked, and the Earth actually gets a shadow, and the sun is completely blocked. We had one here at Lee a couple semesters ago. Pretty spectacular. Very rarely do you ever get to see an eclipse like that. And we just happened to be at the right place at the right time. In a couple more years, and a couple miles down the road, we'll have another eclipse that'll happen. And then after that, it'll be hundreds of years before this area gets another one. A lunar eclipse, on the other hand, actually happens a lot more often. The sun is here, the Earth is here, and the moon is here. Now, the moon is really tiny, so I only get a little tiny shadow, and that's why solar eclipses are hard to see. The Earth is huge, and so you get a big shadow, and a lot of times you can see lunar eclipses because the shadow of the Earth is much larger. And so eclipses are pretty spectacular. Here's a animation or a video about eclipses that talk about this in just a little bit more detail. That was kind of ironic about if you actually listened to the BBC clip on the 1999 eclipse. They said, oh, we're getting pictures above the clouds of this total eclipse. So they were out there, and it was England, so it was cloudy. They totally missed it. They got to see it on a TV screen. And we were kind of worried about that here. It was just partially cloudy, and the cloud just moved out of the way so that we could see the total eclipse right out here. We had our big telescope out, and we were looking at it too. The surface of the moon has lots of craters, right? And so the craters are a particular feature where there were lots of meteor strikes. And because we have no erosion on the surface of the moon, they have been there ever since they were made, and they can be seen. Because we are so close, we should have been hit just as many times. So let's take a look at the surface of the moon. The moon is not made of cheese, and there is not a man's face there looking down on us. But it is the impacts of craters that have created what we see on the surface. The maria are those dark areas in which an impact cracked the crust and magma came up through and solidified, creating a much different type of rock that was there, much darker. The very light areas are mountainous regions from more recent craters. And when we went to the moon, we aimed for the flat, dark pieces, not the light mountainous regions, so that we had a place to land and not tip over, because that would have been bad too. There are ideas about how the moon came to be. One, that the Earth was larger and it ushered forth a little bit of its material to create the moon. The second, that the Earth was there and the moon came by and it got trapped in the orbit, and now we captured a moon. That as the material formed to collect the Earth, there was also material that formed to collect the moon, and they formed together right next to each other. And the last was that the Earth was a little bit smaller, the moon was a little bit bigger, and that at some point in time they collided. They mixed up material, the Earth became larger, the moon's material became smaller, and that's how the moon formed. So these are ideas. One has been more accepted than the other, and we'll show you who came up with that. Or I'll try to show who came up with that. Well, that broke up. Okay. So he was excited to see his theory, after lots and lots of years, actually be accepted. The last idea is about tidal lock, meaning why does the moon orbit the same speed as its day? And it's because of how the two gravities work together. All right, and that explains why that balance between the gravities keeps one side of the moon facing us at all times.